We're in Rosen, Discrete Mathematics and its Applications, section 1.5 on nested quantifiers, and we'll do some statement translation using the nested quantifier concept. First, we're going to look at a symbolic statement, symbolic proposition. For every x, c of x, or there exists y such that c of y and f of xy. So since the parentheses are around the entire statement after the for every x, that means we'll evaluate that entire statement for um, each x, and that this x and this x are the same every time. Okay, so C of x is defined as x has a computer, f of xy is defined as x and y are friends. What does this statement say? Oh, in the domain, these are students at your school. So for every x, C of x means that everybody at the school has a computer, or there exists y such that c of y and f of xy. So the way to write this in English would be every student in your school has a computer or has a friend who has a computer. Okay, and we're going to take advantage of our propositional function f of xy above and look at a three variable nested quantifier. There exists x such that for every y and for every z, f of xy and f of xz and y not equal to z implies it's not the case that f of y is z. Well, not the case that f of y z is x and y and z are not friends. Here y not equal to z means when y and z are not the same person. Because it's possible when you're looping through y and looping through z to encounter the same value, and we have to account for that fact. So this basically says that there's a person, x, such that if he has a friend in y and a friend in z, and they're not the same person, then y and z are not friends. So there's a student, none of whose friends are also friends with each other. Okay, so let's look at a more numerical one. The sum of two positive integers is always positive. I want to put that into a logical symbolic expression. It's a good idea to try to rewrite it to capture our logical connectives and quantifiers. For every two integers, we'll have a nested universal quantifiers. And if they're positive, then their sum will be positive. And then we can introduce variables for these integers, x and y. So sorry, for all positive integers, x and y, there's our two. X and y is positive. There's the conclusion of our implication. And so now that we have our variables, we'll introduce our quantifiers and a test for whether they're positive or not. So for every x, for every y, if x is positive and y is positive, then x plus y will be positive. And we do have to remember to specify the domain. All right, so here's another one. There's a woman who has taken a flight on every airline in the world. Here we're going from English to symbolic representation. And we're going to need two, or at least one way to do this is with two variable propositional functions. One of them is going to be P at W and F, where W has taken F. W comes from the set of all women. F comes from the set of all flights. And then another propositional function, Q at F and A, where again F comes from all flights and A comes from the domain of all airlines. So Q of F and A is F is a flight on airline A. And there's our domains. And we can write this as there exists W such that for every A there exists F such that P at WF and Q at FA. So there's a woman who for every airline there exists a flight such that the woman has taken that flight and the flight is on that airline. And that is some examples of translating nested quantifiers.